one of them is when it's charged, and one of them is after it's been protonated.
Oh, okay.
You've got an
Gotcha.
acid environment, so
Gotcha. Okay, that makes sense. Thank you.
yeah. Did everybody's get graded wrong? Did somebody get number 2 correct?
Well, I was talking to my friend Emma and I said, I don't know what I did wrong, and that one, she said, oh, that's the one I put, and I got it right.
Okay, cool. Good, good. Number 2.
Yeah, that's it.
Okay, cool. I'm just making sure that.
Yeah, I think it just might have been mine.
Better that, one of them got graded a little too quickly, and then we can fix that. You know what? Let me write that actually in. Let me sign that or something. That way I can add your 2 points back.
Thank you.
Yeah, turn that in with your corrections, and I will fix that. Actually, I'm gonna write on the front. That too. There we go. That way I won't forget. If I don't look at the pages. If you guys want to turn in your test corrections on paper, you can turn them in up here. That would have been really smart of me to have a stapler.
I can go check out there.
Okay. If you find a stapler out there, cool. If not, we can all have the field trip to my office for a stapler. Or where to? Sorry? Oh, right over there on the, yeah, thank you, sorry. Or just either way, honestly. All right.
Turn in test corrections.
Test corrections, please.
I paper proof from the other side.
Oh, okay. Awesome. Okay, that works. Just. Yeah, as soon as I got here, I was like, oh, I should have a stapler. Nobody ever has a stapler. Why would you have a stapler? Because, you guys have to carry around all your stuff.
I have my name on both. Is that sufficient? And if
That
that's together.
Yeah, if you've got your name on everything, then that works for me. And I was, no, put your name on every piece of paper, and just at the top, and then just turn in all lumped together, and I will staple them. Because that's on me. Stapler is in my opinion, a my responsibility thing and not a yours, because these things are heavy and expensive and only worth keeping around if the department buys it. And not me specifically. All right. Yeah. Okay, cool. So, test corrections are due today. I am holding the key until 12:30. I have the online thing set to close at 12:30 or 12:40. I have it set to close at 12:40. So I'm gonna wait until after that closes, and then you physically won't be able to submit anything on there anymore, and then I'll post it unless somebody needs a little bit extra time and they let me know. So we're going to talk about dienes, conjugated systems, and pericyclic reactions. We're going to do a lot less mechanisming even than I had planned. We're going to do the DL Holder mechanism, which we kind of did a crash course in, you guys did in lab. And the other 2 mechanisms we're totally going to skip, but we'll look at what products they form. Or at least we'll skip in terms of you guys won't have to know it. In in all my wisdom, as I made our schedule, so I kept looking at these. These are just like where I took out answers to problems that I kept in here, or any like mechanisms or reactions or anything that I like took out of the slides, for at least took out of your like pre-lecture slides or took out of like the lecture slides so that I still know what's going on. And chapter 22 is like several pages, and chapter 21 is only this, and chapter 20 is only a couple pages. Yeah, only a couple, and I'm kicking some of this out, and most of it's not mechanisms. So I was like, yeah, chapter 22 will take longer to get through. Chapter 21 must be short. And slide-wise, 20 and 21 are way bigger than 22. So, we're gonna hopefully go faster. But I know I always say that. It's gonna be fine. We're gonna get through stuff, and there are things I'm willing to skip in these, so. And by skip, I mean completely take off of your, exams when I skip them. So, let's talk about stability of conjugated dienes. Did you talk about conjugation in first semester at all, or is that just a word I started using at some point? I've used that word before, right? Did I ever stop and explain it, or did I just start using it, and we went with it? I feel like I just started using it. So I apologize for that. Conjugation, basically, whenever you can draw, I want to say, dienes, okay, before conjugation, fine, whatever. I'm going to go with conjugation is, it's often described as, there's conjugation when you have a double bond every other bond, right? If we have this, well, one, I drew it wrong, because this is a carbon with all 4 bonds, right? But only 2 things bonded to it, no lone pairs. So really, that's the geometry of this, right? This guy is not conjugated. So basically, whenever we can do, whenever things are every other, whenever it starts looking like, oh, we could start drawing some resonance structures, that's when you've got things that are conjugated. I guess it's, I don't know, I like to think of, no, I guess you can draw, I guess technically this lives like this, and you can draw a resonance structure like this, where you get the charge separated. So that's not resonance, right? There's just one double bond. So resonance is, I guess, when there's more than one double bond, and you can do, or conjugation is when there's more than one double bond and you can do resonance kind of among them. Or, yeah. Is that all conjugation? Double bonds separated by a single bond. Double bonds that share an sp hybridized. Oh, cumulated dienes. Cumulated dienes is the word for this, where they share an sp hybridized carbon. So, this is sp2, right? It's bonded to, well, presumably a hydrogen up here. This guy is probably sp2, it's got 2 things here. This guy is sp, right? And we talked about, the other day when we talked about triple bonds, the way that they do things, yeah, I'm gonna do this again. We get, these guys have, let's see, that's a p orbital, and there's overlap. And then the p orbitals that these guys are participating in are like, let's see if I can do this. That is coming out of the board. Does that look like it's coming out of the board? no, you know what, we're gonna do this instead. We're just gonna go, it looks like this, because it's coming straight out of the board, so it looks like a circle. So these guys have their p orbitals blending together on, like, up here where we can see it, and this guy has this going on. Yeah? That can't be conjugated. This guy's flat, so if we look at, we're just gonna draw little lines where carbons are. This is kind of what it would look like on its side, right? And we have a bunch of p orbitals that are participating in this bonding. So in this case, we've got bonding there, and bonding here. But, I mean, really, every carbon here has an orbital in this p or pi, like, above and below kind of situation, right? None of them are sp3, where it would, like, not be flat anymore and not have the ability to have some above and below planar stuff, right? Basically, conjugation is just sort of, these electrons are a little more smeared, or they can be. So when we represent it like this is kind of what we mean. And like, yes, this bond, like if you get an actual, if you get a crystal structure, that's like the closest thing you can get to looking at an individual molecule, you will see like double bonds stronger are shorter, right? You'll see that these bonds are slightly shorter than these bonds, so they're not entirely shared, right? But these bonds are going to be shorter than most normal single bonds, and these bonds are going to be a little bit longer than most normal double bonds. So there's just sort of a lot of, when we have every other, this pattern, there's a bunch of electron smearing that's just sort of kind of able to happen. Because there's this nice pi bonding area above and below the planar molecule. Yeah? And just sort of smear around. I don't know, I like describing it that way. So these are the two types of dienes. Well, okay, three types of dienes. We have the ones that I don't care about, the unconjugated dienes, and then we have conjugation when we have this pattern, and then we have, oh wait, I shouldn't have drawn it like that, it's actually planar. No, that can't conjugate, we're doing like this, and that's not gonna hang out. So, basically, whenever we have p orbitals that can kind of overlap or are going in the same direction, so even though these are the ones that are overlapping because there's bonding, these are all in the same area, and you can just sort of make it overlap, right? Like they're all set up nicely to overlap. Then they do end up overlapping, and we get conjugation. So, stability of conjugated dienes. Let's talk about heat of hydrogenation. I think we brought this up. Yeah, did we bring this up? Did I bring up heat of hydrogenation or something else? No, I brought up bond dissociation energy. I think those are opposite. Have to look that up. Okay. Heat of hydrogenation, basically, how much heat would be released if, like, theoretically, how much energy is released in kilocalories per mole in heat if we sort of, what is it defined? Oh god, it's thermodynamics. It's one of those some things that's not exactly if you just burn it, or I think it's if you broke every bond there. I want to say is if you break every bond that's there. That might be your theoretical heat of hydrogenation. Like that. You can measure hydrogenation. Morning classes. Okay, I'm sorry. I was trying to relate this to bond dissociation energy with just bonds. Heat of hydrogenation, it's right there in the name, hydrogenation. Yeah, hydrogenation is just when we, hydrogenate all of the double bonds, like in, hydrogenated fats, right? Hydrogenated fats are fats that used to have some double bonds in there, and then we broke that with, the easiest way I can think of, so probably the way that it's done is just with hydrogen gas and a transition metal catalyst. So basically, if you were to take any of these guys and hydrogenate them completely, so add as many hydrogens as necessary, and break all those double bonds so that everything's a single bond and all those carbons are sp3, that's how much heat is released. That's much easier to measure than whatever I was trying to figure out earlier. So, we can measure this, and then we can also sort of calculate it, like what it should be, right, theoretically. So, relative stabilities, basically, I don't. Okay, yeah, like, most of these I feel like are not super worth looking at, but like, right here, this is really what's interesting, and I don't know why they give you a whole table. But here we've got two double bonds, right? Heat of hydrogenation is 60.8 kcals per mole, and here we've got the exact same thing, but we moved that double bond over one. This guy is conjugated, right? Because we've got that every other pattern. That's 54.1. So less heat is released when we, no, heat of hydrogenation takes heat to hydrogenate it. Negative means, negative delta H is exothermic, so it releases heat, right. So this guy, this is a higher energy compound than this, right? Like, we're taking them both down to, they have the same number of carbons, so it takes more energy to break both of these than it takes to break this situation, which means this whole thing is lower energy, this is more stable, closer to where they all end up, right? Does that make sense? Lower energy, more stable. If we predict the heat of hydrogenation for 1,3-butadiene, we can kind of do that because generally, because we can take this, right? We can take one butene, and then we can just hydrogenate that and then multiply it by 2, right, for 2 moles of that. And it looks like we should get something about 254 kilojoules per mole, something around 60.4. But then when you actually do this with 1,3-butadiene, you get 237, 56.5. So a little bit lower. So this guy, this dude is a lower energy compound than this guy. Does that make sense? Okay, lower energy, more stable. So more conjugation you have, the lower energy you have, the more stable everything is. Yeah? And they give us a nice graphical. It should be about, this 2 times this guy should give us around here, but oh, it's slightly below that. And so this is like a measurable, like conjugation isn't just something we made up. Like, oh, whenever there's every other double bond, we pretend that we can scooch the electrons over. Like, there's a measurable difference in stability, and it is, to an extent, more stable to have conjugated double bonds than it is to have random double bonds. So, orbitals. Have you guys, did you do anything with molecular orbitals or molecular orbital theory in first semester? Like Vesper? You guys did Vesper stuff, right? Okay, Vesper, this is kind of that, but yeah, so this is gonna be, is Vesper molecular? Vesper is atomic orbital theory. Yeah, Vesper is atomic orbital theory. This is molecular orbital theory, which is basically just, we use the atomic orbitals and smush them together when there's bonding. And there we go. So, basically, p orbitals, whenever I drew them, I didn't actually color them in, but usually they're colored in, or at least one side of them is shaded, because they've got two nodes and they're like polarized. Like it matters if it's going this way or this way, hence the colors. So, when we have, this is all 1,3-butadiene, that, there we go, that's better. That's the sky. So, seen from the side, 1, 2, 3. Yeah, those are totally carbons. This is just flat. Okay, so, in figuring out the molecular orbitals, like how many molecular orbitals there are, we have like a